Yeah. Okay. So the concept that we are pursuing is limit continuity and differentiability. So that is the idea that we are kind of proceeding on. Now I have a kind of XY plane. On the XY plane, okay, this is x-axis and this is y-axis. This is x-axis and this is y-axis. Now xy plane, there is any point that we can see blue color. This is a comma b, and for every x and y, there is a function over x and y, that is fxy. That is the z value. That is the vertical value that we see. Now I have to prove that function is continuous. First thing, continuous at this point a comma b. If you want this continuity, then we have to calculate the limit. Limit means function xy. Okay, so suppose that a comma b. What is the value of function at a comma b? Suppose the value of function at a comma b is L. Then fxy, when xy tends to a comma b, when xy and ab are very near to each other, infinitesimally uh, close to each other, their delta x and delta y between xy and ab is very less. So if xy tends to a comma b, then fxy should be L. That is continuous function. So what it means that fxy should be equal to fab as far as limit is concerned. So if we want to see that, okay, as far as a limit is concerned, then what are the these things? Okay, so we talked about uh, uh, directly proportional, we talked about inversely proportional, and we talked about constant. So if fxy is fx, the value of fxy when xy is nearing to a comma b, then what is the value of xy? It is seen. If it is directly proportional to xy, this is what we want. Means if xy is going towards a comma b, suppose a comma b is 0, 0, then x is decreasing. If x is y is decreasing and fxy is directly proportional to x and y, then fxy is sensible to x and y. If it sensible to x and y as directly proportional means the way xy is changing, fxy is also changing. So there is a smooth transition of fxy near AB. If it is inversely proportional means fxy would change opposite the way xy is changing. If xy is going towards 0, 0 means xy is decreasing, then fxy would increase heavily. If xy is 0.00001, then fxy is in thousands and multi-thousand. So when it is going to the origin, drastically it is increasing. So this is what we don't want. So if fxy is inversely proportional to xy or fxy is constant, those things we don't. Fxy should be directly proportional to xy. If that is the case, then we consider that fxy is continuous at point a comma b. So this is continuity. Now we calculate now the fundamental of differentiability. If a function is differentiable at a comma b or not. Differentiability means that the function, the rate of change of the function in all the directions. If it is x and if it is y, then in all the direction. Okay, so I can make it even darker. I believe this color. Okay, now it is clear. This is xy plane, then this is a comma b. Now if I approach from all the direction to a comma b, then the rate of change, okay, the rate of change, what we see, rate of change in a way that dz by dx, dz by dy, that is one thing. Or along any, this is the rate of change of z along x-axis, along y-axis, or along any vector. The change what we are seeing at a comma b, that should be continuous. That should be definite. If rate of change is definitive and that is predictable, then it is differentiable. Now, we cannot. Now we have seen so many discussions that if we have orthogonal components, then no need to run for all the directions. Only orthogonal component is enough. So x and y is enough. So if I approach from the x-axis and if I approach from the y-axis towards a comma b, and if I see partial derivative fxy, partial derivative fyxy, these two we have to see that they exist or not. So if partial derivative, that is dz by dx, partial derivative, that is dz by dy, if they exist at a comma b, then partial derivative exists. If partial derivative exists, it is continuous, then we are one step more toward the differentiability. But idea is that if I say partial derivative along x-axis is there, partial derivative along y-axis is there at point A comma B, but I want both to be simultaneously exist. So the only place they exist simultaneously is called tangential plane. So suppose that this is my 3D. Okay, this is papaya, and this is my 3D. So at any point, if I calculate the tangential surface, so suppose this is tangential surface. Now the point A comma B is here. Same point A comma B, it is touching the tangential surface here. Okay, this is what deliberately it is being done. Okay, now it is like this. Can you see it clearly? So at point that is dot here, A comma B, there this 3D is touching. Okay, after that this 3D is going upward. Okay, so if I show, okay, now here it is going upward, where tangential surface is in this direction. So tangential surface direction, so only at point A dot B, the tangential surface and the 3D, they are same, only at this point. After that, they are different. So surface is going in this direction and 3D is going in this direction. Okay, now the equation for the tangential surface at A comma B, if I go for the equation, that is Lxy, that is new kind of dependent variable function over xy, that is Lxy. Whereas the graph function at A comma B, the function is fxy. So fxy, Lxy. So fxy, whatever is the graph function. Whereas Lxy is, if it is passing from origin, then it is mx plus ny. Mx plus ny, where m is dz by dx at point A and n is dz by dy at point B, or dz by, or fxxy, fxab into x plus fyab into y. fxab means, fx means partial derivative along x-axis at point AB into x plus fyab into y. fyab means partial derivative along y-axis at point A comma B. So Lxy equal to fxab x plus fyab y, but this is not complete. If we are talking about AB point, then AB point we have to consider. We are considering origin, but we are doing everything at AB. If that is the case, then it will come to general formula as z minus z0 equal to m x minus a plus n y minus b. Because if it is passing at a comma b, we have shifted origin to a comma b. If we have shifted, then x will be x minus a, y will be y minus b, and at ab whatever the z is, so suppose it is z0, then it will be z minus z0. So z0 is nothing but fab. At point ab, what is the f value, z value, that is fab. So z minus z0 equal to fxab x minus a plus fyab y minus b. Okay. So z minus z0 equal to dz by dx at point a comma b into braces x minus a plus dz by dy at point a comma b into in braces y minus b. Now z0 is nothing but fab. So if z is lxy, that is the tangential surface equation, then lxy equal to fab plus dz by dx at a comma b x minus a plus dz by dy at a b y minus b. Z equal to Lxy, the tangential surface equation equal to FAB, what is the function value at point A and B, Z value, plus Fxab x minus a plus Fyab b minus y minus b. Fxab is dz by dx at point A comma b. Fyab is dz by dy at point A comma b. This is the tangential surface. This tangential surface contains both the partial derivatives. So now idea is that the graph should be continuous at point A comma B and both partial derivatives should be altogether should exist. It exists now in tangential surface, but problem is again limitation, limit. Now we have two surfaces. Can you see? One surface is this and one surface is sphere. They meet at point A comma B. Otherwise, they are different. How much they are different? As we grow, we are seeing. So as we grow, okay. So as we grow in direction, the gap between this is growing. Here the gap is this much. Gap is less. Gap is less. Gap is less. And at A comma B, there is no gap. They are same. But as we grow, tangential surface grow like this, and so whatever the gap is, we call it error. But anyway, now if tangential surface is going towards A comma B and the main graph is coming towards A comma B, so they should be equal when they should become slowly they should become equal, and they should be exactly equal at point A comma B. So the LXY, that is the tangential surface, when XY tends to A comma B, when LXY, that is the tangential surface, LXY, in continuous we saw that function fxy when xy tends to A comma B should be equal to FAB. Same thing here. LXY is carrying both partial derivatives. This is required. Anyway, it is continuous that we have seen. So LXY when xy tends to A comma B, then its value should be near to FAB or equal to FAB. This is limit. And if this is the case, if it is satisfying, then it is differentiable because both partial derivatives exist in the tangential surface. So if tangential surface limit to the graph equation when xy tends to A comma B, then it is differentiable. Okay, so the condition for differentiability is that it should be continuous at that point and both partial derivatives together should exist at that point. So together they exist only in tangential surface equation. Now tangential surface equation, if it has to follow the rule or regulation of limit, then when x and y tends to A comma B, when it is approaching A comma B, if it is very near to A comma B, then Lxy should be equal to Fxy. If that is the case, then it is differentiable. Now we talk about, there are two things that is coming to the picture. Continuity, there was only Fxy. Here Lxy, Fxy. Two things are coming, tangential surface and graph. So now if I consider this as error, okay. So if I consider this as error, then error slowly, this error, the way the okay, the way the surface, the graph is the more 3D model, it is going up. Can we see where a tangential surface is here? So slowly the gap between the 3D and tangential surface is growing. So we can say now gap is this big, gap is small, gap is small, gap is small. So this gap we call it error. So error equal to fxy minus lxy, or or f or fxy equal to error plus lxy. So error what we see is fxy minus lxy. This error when it is near xy is nearing to a comma b should be 0 as per the limit. Now there are 2 points. Suppose one point is a comma b, another point is a plus h, b plus k, or delta x delta y. This is the way we calculate differentiability. This is the way, anyway, we calculate the differentiability. For differentiability, we at any point a comma b, we calculate the function value at a plus delta x, b plus delta y minus fab divided by delta x square plus delta y square square root. This is the differentiability. Normal, right? Means if it is single dimension, then f a plus delta x minus fa by delta x. If it is two dimensional, then fa plus delta x b plus delta y minus fab divided by delta x square plus delta y square square. Now, if I am talking about error, okay, if I am talking about error, then it is f. Now we are at 2 points. One is a comma b and one is a plus delta x and b plus delta y. Okay, so that is the delta x and delta y are infinitesimal small and they are very near to a comma b. That is limitation. So lxy when xy is nearing towards a comma b, okay, or when h and k, so I am calling lxy when xy is nearing toward a comma b is f, okay, so is so nearing toward, but where exactly it is? It is exactly at a plus h. Suppose h I am calling delta x and b plus k is delta y. So we calculate the error at a plus h and b plus k, or a plus delta x, b plus delta y. There we are calculating the error, and that h and k we are reducing to 0 because h and k are delta x and delta y. Actually we should be doing x and y, they are moving towards a comma b rather than xy moving towards a comma b. Now there is one point a comma b, there is another point called a plus h and b plus k. This is the how we calculate the differentiability. We calculate the dependent variable as these two locations and independent variable as these two locations, and we divide. That is the differentiability tends to 0. Now, if I want this error, whatever error we are saying, if this is the tangential surface and this is the model, then this is the error. Error is reducing. Now, error at point at a comma b, tangential surface and 3D model are same. So, at point a plus h and b plus k, okay, if that is the point, then if h tends to 0 and k tends to 0, then error should be 0, or lxy where xy tends to a comma b should be f a b. If lxy, okay, lxy when xy tends to a comma b, it should be equal to fab. Then error is fxy minus lxy, then error should be 0. Same thing, fx, fab and lxy when xy tends to a comma b are same, then fab minus lxy when x minus x comma y is very near to a comma b is 0. If I call fxy and lxy, fxy minus lxy as error exy, then e error at a plus h and b plus a plus h and y plus k, a plus h, a. Okay, so suppose we are doing at a comma b. So error at a plus h and b plus k, where ab is the point we are taking for differentiability. So error at a plus h or a plus delta x and b plus k or b plus delta y, where h and k they tends to 0, then it should be 0. Error should be 0. There should not be any difference between fxy, fab and l a plus l a plus h b plus k. Okay, so error, what we are saying, should be 0 when the tangential surface and the 3D graph they are meeting at point A dot B in and around infinitesimally small distances, that is h and k. Okay, if h and k tends to 0, then they should be equal. Can we see the similarity between this and continuity? But anyway, now the error, what we are seeing, error at a plus h, b plus k, where h and k tends to 0, then it should be 0. If I am able to prove it, the way I prove the continuity, that fxy when xy tends to a comma b is equal to fab, then that is directly proportional to the xy. That is what we saw. If here also, if you see directly proportional to h and k, here h and k is the variable. There xy was the variable. Here h and k is variable. That is delta x and delta y. So if a comma b, that is the point on the xy plane, we are trying to calculate the differentiability of the function fxy. That is the problem. If we want to calculate the differentiability, and if lxy is the tangential surface at a comma b, then at a comma b lxy will have same value as fxy, because it is tangential and they meet at that point. If that is the case, then at that point the difference between fxy and lxy should be 0. If fxy minus lxy is the error, then error should be 0 there at a comma b. Now, if I say if error at a comma b, EAB is 0, then what is error at EA plus h, b plus k, or a plus delta x, b plus delta y? What is error there? Whatever the error is there, if I say h tends to 0 and k tends to 0, then it should be equal to 0. Error should be equal to 0. If that is the condition we carry on, then if you are able to prove it, then it is differentiable. Okay, let's take example that it is really differentiable or not, like a paraboloid. Okay, fxy equal to x square plus y square. That is paraboloid. Okay, this is like paraboloid. Okay, at the origin, from there x square, from y square. So both are growing like anything, and here at the bottom the tangential surface is 0 in x direction, y direction, because they are parallel to x axis and y axis. Otherwise, at other places there is really tangential surface, but here at the origin it is 0. If this is the origin, if this is the origin, then tangential surfaces are 0. Now we are saying that error at a plus h and b plus k, whatever error we see, it should be 0 if h and k tends to 0. If that is the case, it is differentiable there. For that, what we are doing is we are subtracting fxy at a comma b and lxy. Okay, sorry, we are subtracting f a plus h b plus k at point a plus h and b plus k, and lxy at the same point, a plus h and b plus k. If we subtract, and it should become 0. So x square plus y square, that is a plus h whole square plus b plus y, b plus k whole square, minus lxy. Lxy is nothing but fab plus m x minus a plus y plus n y minus b, fxy minus lxy. Xy now is a plus h, b plus k. Okay, we are trying to find differentiability at point a comma b. If you I want differentiability at a comma b, then very near to a comma b there is a point called a plus h comma b plus k, where h and k are delta x and delta y. A plus h and b plus k are 2 points that is very near to a comma b. If that is the case and h tends to 0 and k tends to 0, then if I subtract, because at a comma b tangential surface and the paraboloid, they are same. If they are same, then at a plus h, b plus h, okay, they should be tend to same if h and k tends to 0. So if at that point, if I subtract f a plus h b plus k minus l a plus h b plus k, then it should be 0. That is the error. Error should be 0. Then what it is? So f a plus h b plus k is a plus h square plus b plus k whole square. And here again minus f a b. Okay. Now see the LXY equation. F a b. FAB is, so A and B we have taken origin because we want things to be simple. So now A plus H square plus B plus K square become H square plus K square. That is FA plus H B plus K. A square H square plus K square minus LA plus H B plus K. So for LXY equation is FAB. So FAB is F00, that is 0, x square plus y square 0 square plus 0 square 0, plus m is dz by dx. So here 2x. So 2x means 2h. 2x, x is a plus h, a is 0 means 2h. And x minus a, x is a plus h, then that is h, so 2h square. Okay, like that 2k square. So it is h square plus k square minus 2h square minus 2k square. Okay, divided by, this is the fundamental of differentiation, divided by delta x square plus delta y square square root. If I want differentiability at any point a comma b, then fa plus delta x b plus delta y minus fab divided by delta x square plus delta y square square root. Here also we are doing same thing. F if we want at a plus delta x, then fa plus delta x b plus delta y minus l a plus delta x b plus delta y divided by delta x square delta y square square root. That is also called relative error. So, or normalized error, whatever it suits people. So f a plus h is delta x, k is delta y. F a plus h plus f a plus h b plus k, a and b are 0, then that becomes f h k, that is h square plus k square, minus l a plus h b plus k, that becomes, for LXY the equation is FAB plus m x minus a plus n y minus b. So FAB is 0. Okay. Now m is dz by dx, that is 2x. So 2x at point a plus h is 2a plus h, 2a plus h. A is 0 means 2h. 2h into x minus a. X is a plus h. Then it is, okay, h. So 2h square. 2h square plus 2k square. Now it is minus, means fxy minus lxy. So it will become h square plus k square minus 2h square minus 2k square divided by square root h square plus k square. That will come as minus h square plus k square divided by h square plus k square square root. That will come as minus, okay, minus h minus a square root h square plus k square. That is the error. Now h tends to 0, k tends to 0. Okay, now we talk that if we are in this situation, then we see it is directly proportional to or not. It is directly proportional. Okay, so the error at a plus hb plus k, where h tends to 0, k tends to 0, is minus h square plus k square square. So it is directly proportional. Now suppose that h and k are same. We are approaching from a direction where h and k are same, equal. If that is the case, then it will come as, okay, minus square root h square plus h square 2. So minus square root 2h, or the kind of, we can say that plus minus h. The square root of h square root of h square is plus minus h, or h minus 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 a square root h, whatever. The error is directly proportional to h. If h is increasing, error is increasing. If h is decreasing, error is decreasing. Means it is differentiable. If E A plus H B plus K equal to minus root 2h, then error is directly proportional to h, the distance what we are taking. Okay, so if it is if it is inversely proportional 1 by h, then when h is decreasing, then error is increasing. When h is 0.00000001, then h is infinite. Okay, then error is infinite. Error should decrease when we come near to point A comma B. Fxy and Lxy, they should be exactly same at A comma B, but they are opposite. They are going as, so if it is inversely proportional or it is some constant, then it is not differentiable, but it is directly proportional. So Fxy equal to x square plus y square. If that is the equation, then it is differentiable at A comma B. Okay, now I would kind of rebind. Okay, so I'll do the binding again. So what we trying to show is that in two dimensional, where we have xy plane and there is a point on the xy plane, if I have a xy plane and there is a point on xy plane and the point is a comma b, if point is a comma b, then if there is a function that is a function upon independent variable x and y, then function is differentiable at a comma b or not. That is the question. Now first we try to find that if function is continuous at a comma b or not. If fxy, where xy tends to a comma b, and fxy is more or less near to fab, then it is continuous. In other words, if fxy is directly proportional to x, then it is continuous. Otherwise, if it is constant or it is inversely proportional, then it is not constant. It is not continuous. Constant we have seen in equation like x square by x square plus y square, where if we see the x direction keeping y as constant or 0, it is 1. This is nicely we have seen. So these are not continuous. You can try xy by x square plus y square. Anyway, we will demonstrate this. So function has to be continuous at 8 comma b, and there are two partial derivatives. One is dz by dx or dfxy by dx, dfxy by dy. Two partial derivatives, if, okay, both should exist. So simultaneously they exist only in the tangential surface. So if I have a tangential surface and if I have a 3D and they coincide at point a comma b, then, okay, then we have to do the math, because tangential surface contains both the partial derivative. That is Lxy. If Lxy is a function over xy, and that is the tangential surface equation. Lxy equal to fab plus m x minus a plus n y minus b at point a comma b. That is the tangential surface. So at point a comma b, this is fxy and this is Lxy, that is tangential surface. So tangential surface and the 3D model, both are different at other point rather than a comma b. If they are different, then their difference should be 0 when they reach a comma b. If that difference is error, then error xy is defined as fxy minus lxy. Okay, so error at error at a comma b is 0, because fab and lab are same at point AB. But at other places there is error. Now other places, if I am at very small distance from a comma b, that is a plus h and b plus k, then error at a plus b and a plus h and b plus k is error a plus h comma b plus k. If h and k tends to 0, if that distance is very small from a comma b, then error tends to become 0. If that is the case, then f a plus h b plus k, okay, minus l a plus h b plus k, where h is tends to 0, okay, should be 0, because error equal to fxy minus lxy. So f a plus h b plus k minus l a plus h b plus k, where h and k tends to 0, should be 0. They are same now, okay, if as they proceed. So we have now new function, that is error function, in terms of x and y. If in terms of h and k, okay, if error is directly proportional to the h and k, then the way error h and k they come near to a and b, same way error should also happen. So if they are coming near to a and b, error would decrease. If they are far from going far away from the a and b, then error should increase. This is what we want. If it is inversely proportional or constant, then it is error is not the what we want, so it is not differentiable. So this is the concept that we will proceed on. So we gave the kind of example of paraboloid where fxy equal to x square plus y square. Now we are calculating error at a plus h b plus k, that is fxy minus lxy. So a and b are 0. We are calculating at origin. So it is h square plus k square minus 2h square minus 2k square. Okay, because fab in lxy is 0. So that is the case, then it will come like h square plus k square minus 2h square minus 2 square k square divided by delta x square plus delta y square square root. So h square plus k square square root. That will come as minus square root of h square plus k square. If h and k are same, then it will come as minus square root 2 h. So error is directly proportional to h. If that is the case, then as we are decreasing the h and bringing it close to 0, error is also coming close to 0. The way it is tied to the h, to directly proportional, it is okay. So the function paraboloid fxy x square plus y square, it is continuous, it is partially differentiable, then finally it is differentiable at x comma at a comma b. This is what we see. So we'll proceed on this and we'll see various other scenario, then various examples that would make it more clear. But as we have said that if you don't understand limit, continuity and differentiability, then calculus is not yours, because that is the pillar stone for proceeding in the calculus. So we'll proceed on this.